Joan is going to be talking about designing the library powering Netflix's QoE with Scala 3. Fun fact about Joan is that the last time he did a talk at SF Scala and I introduced the speakers in person was here at 2B in 2018, I think, right? Or 19?
19, yeah.
2019, there you go. So welcome back. Over to you, Joan. Thank you so much.
Can you hear me? Good. All right.
Is this working?
I think it's working. It's good. It's good. Yeah, my name is Joan Goyeau. I'm a senior data engineer at Netflix, and more specifically in the Playback data systems team. We're using Scala. And so, as you said, I presented 5 years ago. Okay. Yeah. So, yeah, I presented here 5 years ago, and the title was Scala Free, what does it mean to us? And Scala Free was not even out. So it was like kind of speculative talk about how things can change for us as a user when Scala Free will be out. So fast forward 5 years later, here we are. We're using Scala Free, and I'll show you some kind of unique features that we used at Netflix for that library.
I can take the mic off the stand as well. It's easier for you.
Sure. All right. It's better. Yeah. So. And 5 years ago, I also showed this slide, which is, so I think it's like a good connection, like kind of like a story that continues. So this is kind of like the same as the CAP theorem for database, but this is for streaming video. So what the theorem says is that you basically want all three. So you want to start fast, have the highest quality, have no rebuffer. That's like heaven. But you kind of like when you pull on one, you have to give up on one other or two, and you kind of play with them. So if you want to start really fast, then you're gonna have to give up some quality, and maybe or maybe you have like rebuffers throughout the play. You can have higher quality, but then maybe you give up on starting fast to build up the initial buffer, or you don't have enough buffer, and then you will have to rebuffer throughout the session. And that works all ways, you know, no rebuffer, give up quality, and so on. And so, yeah, at Netflix, we believe that we can pull on all of them as much as possible. Obviously, we kind of have like maybe different approach than YouTube, for example. YouTube, you kind of like when you watch a YouTube video, you want it to start fast. It's kind of more manageable to have rebuffers during the video. I think for Netflix, it's more acceptable that it doesn't start right away, but it's unacceptable to have rebuffers throughout the session. So like the strategies are going to be different. So since we believe that we can push on everything, what do we do? How do we do that? Kind of like many companies, we're data driven. So we run a lot of A/B tests. And when we run those A/B tests, we are collecting data, nothing really crazy. And so we're collecting data. So here's a kind of like super high level and super simplified kind of like super high level architecture. Like, okay, you have devices on the left. We also have our own CDN, so which is on the lower left part of the slide here, and they all log data, and then those things. Okay, we have like playback logs. That's logs that come from the player, like play, pause, rebuffer, all the events that happens during the thing. And you also have like UI logs, UI as in the catalog when you browse the app to choose your movie. That's a UI, so that's a different logger. Now we're a gaming company, so we have also logs from game. We also have CDN logs, and there's many more. I just like tried to add some here. And those logs are used differently. We have quite a bit of Flink for stream processing, also some Spark. So most of them are just like, okay, streaming QoE. You use the logs for assessing the quality of experience of the stream. Same with the app, same for the games. You calculate some metrics out of it. The AC simulator here, AC means adaptive streaming engine. This is the little code that is on your player that is going to select the quality depending on your connection. And also it's going to select which server to download the media from. And it's constantly running as you play a movie. So this team that developed this adaptive streaming engine also has a simulator. So I just put it there because it's an interesting use case where they're consuming also playback logs. And the simulator is that they can basically replay the logs. They're consuming also like potentially CDN logs and so on, and they can replay a million sessions, for example, with a different code, a different algorithm, and see if there is less rebuffers, and without even like we don't have to deploy it in production for a set of people. We just replay the logs with that new thing, and the output would be like, okay, is the play delay still small? Play delay is the delay that happens between the time you request a movie and it actually plays. So we want to like shorten that as much as possible. So that's a cool use case. You can do it like pretty quickly. So what are the challenges? So we have quite a bit of sources, log sources. We have a few apps that are calculating QoEs and stuff like that. And every time on Slack, it's like, hey, how do we calculate play delay? What data are we using it from? It's like constantly a lot of questions around how do we do things, basically. And newcomers also come and are trying to understand things. And it's data engineers, it's software engineers, front ends that are trying to deploy something and know if it's doing better. It's the adaptive streaming engine team, it's AEs, it's like a wide range of users, which are trying to understand how things work, basically. So discoverability is a challenge. And then once you discovered things, the challenge is how do you, okay, you identify a bug, you want to contribute a new measure, a new metric. How do you do that? So you have to identify first where it is. You have to check out the repository. You have to like set it up on your laptop. It's probably it's a lot of hassle. So contribution is kind of a barrier. And then there's also reusability. So in the previous schema, when I spoke about the adaptive streaming engine simulator, the simulator kind of wants to calculate the same metrics as the streaming QoE. So we kind of like want to compare, is this better than the previous one? So we kind of like want to run the same code that will calculate the play delay, the rebuffers, all those things. So we want reusability kind of. So it would be nice if it was in the library. We did it, and this is what this talk is about. It's about measures library. So we called it measures library because for us, there's distinction between metrics and measure. It's not called metrics library because a measure is like you measure a play delay. So okay, for this viewing session, your delay was like 1 second. That's a measure. A metric is when you aggregate it. So okay, over time, did the play delay go up? That's a metric. And the metric, there can be many metrics for one measure. You can, depending on how you aggregate it, do you do average? Do you do percentile? All those things are different metrics based off the same measure. So the library is only focused on measuring things. So what is measures library? It's kind of like simple functions. You put data in, you get a measure out. That's it. We want to enable composability. So meaning that you can have a function that gets some logs in and calculates the play delay or the number of rebuffers in a session, things like that. But you want also to be able to depend on each other. So like, okay, now I'm calculating another measure and I want the input from rebuffers, like, I don't know, like how many rebuffers you had. So it will be a count. And then you want to know if the session was, does it have a Boolean? Does it have rebuffers or not? And so you would want to consume the other measure, kind of like, so you can compose, it's like building blocks, basically. So it's composable. It's easy to contribute because everything is kind of centralized and we kind of standardized everything. So once you learn one thing, you can contribute to it easily. You set up one repo. We actually are setting up some code dev workspace. So you don't really have to set up anything. You just click. You have a VS Code in your browser. So it's easy to contribute, and it's also, we'll see after, but it's also efficient. There's a spoiler alert here, caching. All right, so let's define a use case, and I'll show you code. Here we have two sources, playback logs and UI logs. I just extracted it from the previous slide. So from those logs, basically, we'll calculate some play traces. So what are play traces? Play traces are events that, like, for example, start you started a viewing session. Play, it actually started to play, like the movie. It rebuffers here, you pause, you play again. Those events are called play traces internally. And then from them, then we can calculate rebuffers, like how many rebuffers you had during the session, the play delay, things like that. And I just put another one, like device model. I don't know. There's like, in that library, there's 750 of them that we're calculating. So there's a lot of them. Just extracted a few of them. Device model. And what's interesting about device model here is that we can derive the same measure. It's kind of weird to call device model as a measure, but it's just a field, you know. But we're extracting it from different source. So a measure can be coming from different source of data. So like UI logs or an actual viewing session. All right. So let's just define some models. I don't know. I massively simplified everything, but play trace is going to be a thread. It's going to have an instant on when the play trace happened. And so basically it's going to, throughout your viewing session, it's going to monotonically increase. You know? And so you have different implementation of it. You have a start, you have a play, you have a rebuffer. There's a lot of fields in them. I just removed everything. But when you have a rebuffer, for example, you have a reason. Why did it rebuffer? The player is actually able to know if it rebuffered because of a network issue or because the device is slow, things like it. There's many, like maybe the CDN was not available. So there's many reasons. Okay, so here's the API. So one would create a file called, let's say, play traces. It would create a type, doesn't have to be opaque type, but here we created one like opaque type. And this is going to be the actual implementation of play traces is a sequence of play trace. And then we're also making it extend the sequence of play traces, so you can play with it. You can do like, give me the first one. Yeah, it's an actual sequence. And then we create a companion object to that opaque type, and we declare a given in there, which will be parser of play traces. So parser is our way to calculate the measure. So here we have a dependency on an object called viewing session. So that's going to be like your row logs. I just like put it in there like this. But let's say it's an object that contains player logs. You can call player logs on it, and it gives you some logs, and you can like calculate the play traces out of it. I didn't want to put like too much code in there, so I just put like parse play traces here. Let's say it's implemented, it just gives you the play traces. And let's note that it's a little bit costly. Like you have to parse stuff from the logs and everything. So let's say you have to sanitize, kind of like go through, the player did not log some stuff, so you have to kind of reconstruct the session. All the devices are not logging the same way, like iOS and so on. We have like a lot of devices. TVs, we support TVs up to like, I don't know how many years, like 10 years. So obviously some features are not there. So we're trying to reconstruct stuff. So this is an operation that is a little bit costly. But at the end of the day, if you give me a session, what this API says is that If you give me a session, a viewing session, I'll give you a parser of play traces. Maybe one thing to note is we're using the new syntax from Scala 3.6, which is like that basically. Yeah, and we have to wrap the code into a parser, so we're calling the apply function here. All right. From that, let's do another one, rebuffer count. So someone comes in and says like, oh, I want to calculate the rebuffers. It's been done a long time ago, but let's redo it. And so what you can do here, you can, instead of depending on the viewing session kind of row event, you can say, oh, I'm gonna depend on another parser. So the previous parser. So you want to depend on the parser of play traces, and then if you have them, then parse a rebuffer count. So notice this is an int here, and so the parser we're just doing play traces count is instance of, I don't know. I put like something quick for the presentation, but the important part here is that we're just calling the apply function here. So I guess the first question is like, what happens if the previous parser is like failing? Well, we'll also fail this one. So we'll come back to the API, to the internal of the API, but this is what we're telling in the like kind of README to analytics engineers and so on. They just have like, we just tell them, create a new file, name it, create an opaque type or create a type, whatever type you have to do, but it needs to be unique. Like you cannot just have an int. You have to have an opaque type if it's just an int. And then define a companion object, put your parser in it, like in a given. Here's another one, play delay. This is a finite duration. Again, same given, same dependency on play traces. And this one gives you a parser of option of play delay. It's possible that the play delay is not here. If you have no events, for example, I don't know, like if you have a start, you never have a play, like it never actually played, you don't have a play delay, so it's none. I put some code in there, but yeah, just for reference, we don't have to dive into it. And the last one, device model. So this one is a string. And what's interesting here is that you have two givens. Basically, you have two parser for device model, but it has different dependency kind of like need for calculating it. So one is depending on viewing session, and the other one is depending on the browsing session, like kind of like the UI logs from different logs, basically. So it will pick one or the other depending on what you have. And that's kind of it for people to contribute to the library. Now, what would happen is that code will be published, and you would run it on your kind of runners. We call them runners. So like for streaming QoE, the app, the Flink app here would run measure library, and others would be Spark. It would run that measure library again. So there's a requirement. It has to be kind of JVM, I guess. So let's see how do they run it. So usually you would have a case class. I don't know, I called it measures here. You would define the measures here. So the notation is like kind of like underscore, because most likely this one goes to a table, and this is the convention for tables. And you would have like, okay, we see again the types that we just declared. So rebuffer count, play delay, device model. We're wrapping them into options. I'll come back to it. And you would have like a given for viewing session. So here I didn't implement it, but let's say we're decoding the events from log, from like Kafka, whatever, and it's JSON. So we just initialize the JSON into this object, or Avro records. We have Avro also. And then what you would do is you would call parser of like your case class, and it will give you parser can be a success or failure. So you match on it, and if it's a success, you get the value. Cool. You do something with it, like you probably write it to the table. You can also get some issues. I'm not going to dive too much into it, but it's possible that your values, you get the value, but some issues has been logged. or it failed. It's just an exception. It's kind of similar to a try, success, or failure. So what did we do here? So we have kind of an API without functional concepts. So no map. You didn't see like map. You didn't see like I mean. So if you're like a developer that does not really understand Scala, you just started. You're like a analytics engineer, and you're like used to do Python or SQL, whatever. You kind of like, you've been told to like, oh, this is the place where you have to contribute. And it's like, oh, now I have to learn like all the functional programming. So we're not using any of that. You just like put empty brackets on it. That's it. And yeah, you just define your dependencies with the given, and you calculate your measure, and that's it. All right, so let's dive into how did we do this. So we used boundary, the boundary API. If you're not familiar with it, I'll try to explain it in the next slide. So before that, let's look at the implementation of parser. What is a parser? So parser is an enum of value. It has two cases. One success, you see the value here, and the issues is an interval of trouble, whatever. Or it's a failure and it wraps an exception in it. We also have an apply function. So this is the empty bracket that you saw before when we were calling the play traces. And here you see, to be able to call apply, you actually need a label of failure. So that using is resolved implicitly, and it's kind of like you see it as a capability of failing. So you can call apply, I'll give you the value, but you need the capability to fail. And so we match on ourselves, and if it's a success, great, we just get the value. If it's a failure, we're calling break. Break is on the boundary API, and break also wants a label of failure. So that's how it gets passed. So you can break only if you have the capability of, if you have the label of whatever that you're going to fail on. And so that mechanism kind of guarantees that if you break, it will be code upstream. We'll see. So yeah, here's the companion object of parser. So we have an apply function. That's the apply function that is being called on the parsers. Like, yeah, here on the right, you have a parser column. We're calling this apply function. This one. We kind of inline stuff, but what's important is that the body of the function actually is it's a context-bound function. So it gives you a label of failure. So in your parser, when you implement your code, you actually have the you have a label of failure. So you have the ability to break on it. And so we get it with the boundary here. So that's how boundary kind of gives you a label of failure. Otherwise, yeah. Otherwise, if we catch any exception, and we'll give a failure, basically a parser failure. Hopefully, it makes sense. We also have a few other things like here. We'll give you a parser of option value if you have a parser of value. So we're just lifting it. It's always going to be some. That's it. It's useful for later. And we also have a parser for any product. And I put question mark here because this is shapeless code. I don't, that's a whole different talk. But yeah, we have some shapeless code that will derive for a case class. So that's why you can get a parser for a case class. It will just derive one if you have a parser for each of the fields in the case class. And something to note is, you know how we put options here? We put everything as an option. We have special handling in there. If one of them failed, like as in throw an exception, well, actually the implementation of the shapeless implementation, kind of like for product, is it's gonna put a none in there and log an issue instead. So that's what the issue is for this list of trouble. It will add the exception in there. So that way we're not like, if someone writes a parser that just fails because they did, I don't know, two ints, it's not an int, it will just not disturb the whole application. All right. Yeah, that's about it in terms of the API. I'll go into optimization now. So here's when we did that, we actually ran into like some poor performance. And one thing that I didn't show you in the component object is that obviously we have an apply function which will look for parser of value and gives you the parser. That's it. Like that's how you like do the syntax, parser of value instead of summon parser value. And so we did that. And yeah, so if we take our example again here, where we're calculating parser, and let's see what the resolution, the implicit resolution is gonna do. So I added kind of like, it's not exactly what's gonna show up, but this is how it's gonna get wired. And let's remove all the other code and let's try to format this. So I tried to format it here. So the first given parser value is gonna be for the product, the one for the case class. It's not exactly gonna be like that. It's not gonna be like flat like this. It's gonna be recursive calls, but let's assume it's flat. It's kind of doesn't matter for this presentation. So the first one is going to be rebuffer count because the case class had a rebuffer count. And then in order to be able to calculate the rebuffer count, you needed play traces. So we're resolving play traces here. And then in order to be able to calculate play traces, we need viewing session, like the row logs. Okay, so we call play traces once here. And remember, it's a little bit costly. Here, we're calculating play delay. And so we have a dependency on play traces. And so again, we're running play traces twice. So this code is like running as many times as it's basically as many times as you have dependencies on it. So yeah, just the app just crashed instantly. I mean, it was just not working. And so yeah, and then you have device model. It's called just once, but yeah. So what we did, we're like, okay, in the parser, the apply of the parser, we kind of like did caching. We're like, oh, we need to cache. Okay, let's create a hash map and just store values in there. It worked pretty well, actually. But then I ran a flame graph. I don't know if you're familiar with flame graphs, but it shows you how much time you spend on each functions. And we were spending a lot of time on hashing. I was like, hashing is pretty easy. How come we're spending so much time on hashing? Well, it turns out we have a lot of measures like device model. It's just extracting something. It's not doing much. So just for that, we're actually hashing, going into the cache and everything, instead of like just literally extracting it from the object. So we were spending a lot of time for nothing into caching. So what did we do? We ended up removing the hash map, and I wrote a macro. I'm not going to show you the macro, but it's called by the summon cache. So we had to inline this function. This is the apply on parser, and this summon cache is just summoning the value just like before, but then it also applies a rewrite of this code, and basically it goes through the syntax tree basically. And macros are executed after it resolved everything. And it took this, and we're rewriting it like this. So basically, we identify calls to like this given play traces. When it's called multiple times, we extract it into a val, and then we put the val, so the cached val here, and that's it. I mean, we saved 20%, so pretty good. 20 to 25. So yeah, simple trick. So let's wrap up. What did we do? Well, we used kind of, it's called direct style, I guess now. Direct style programming for easy contribution. Basically, anyone can contribute without really knowing how to do functional programming. And yet we kept kind of the safety of get the value out of it, but still you're in a safe space to get the value out of it. So usually you would just like flat map, whatever, and have a full comprehension to make it look like you're not mapping over things. Yeah, givens, we use givens for automatically wiring parsers. It's going well. Like it's easy for Java developers because usually we say, oh, this is like Spring AutoWire, but it happens that compile time is safer and so on, and most of the people get it. We used opaque types for zero runtime overhead types. We don't always use opaque type. I know with this presentation I showed a lot of opaque types. Opaque types are for like easy type, maybe like int, boolean, and so on. So everything is typed. It's pretty cool. And it doesn't have runtime overhead. And then we also use the macro for better caching. Yeah. Future work. I showed you this kind of use case as a graph. We're actually looking into building a UI for this. And the way we're going to do it is we're actually going to write a macro that is going to analyze the code and look at all the dependencies and basically build this file that would have the definition of it that we would publish as part of publishing the artifact. And we'll have a team that is going to build a UI, and it will show like probably it's going to be a graph. We didn't do it yet, but probably something where you can click on things and you can browse the dependency tree of like all those things. And then what would be cool is if we use something like source code where you can like, okay, play traces, cool. I want to know how it's implemented. You click on it and it sends you to GitHub. And it sends you to the exact line of where it's defined with the commit and everything. So that's what we're looking to do. That's it. Yeah, if you have any question, please ask any question if you have any. Sure. Wait, I think they're going to give you a microphone.
How about the complexity of metrics? Is it like a simple list, like tens, or is it like something very complicated when you have like hundreds of different metrics that you need to measure from the user experience?
Impressions, you said?
I mean the complexity of metrics. How many different things you are trying to measure?
How complex the measures are?
Yeah.
Okay.
You give a few simple examples, but maybe
those examples are pretty simple. I mean, yeah, in terms of we do have like this one. It's across multiple packages. It's a whole package. So there's an entry point to the given, but then we're doing a lot of things to make it like look good. In terms of look good, in terms of the data look good, because we have a lot of discrepancy between like logs. Logs are not perfect, so some of them are really complicated. I'll give you another example. Rebuffers. Here I give you rebuffer count. It's not an int. It's actually a case class here, and the case class is called rebuffers. It has a subclass called rebuffers.metrics. It has the count, it has the total duration, and then it has other substructs where it's like categorized per if they're late or early. So an early rebuffer is a rebuffer that happened within the first 30 seconds. That's more acceptable than a late one after 30 seconds. It's like unacceptable. So
so actually it is like much more complicated. Just not simple count, but like it is for the full structure of rebuffering, for example, here. So count, first time or not, like time to do. So it is like Okay, got it.
And then we also categorize it by reason. If it's a network issue, a CDN issue, your device can lag also. Sometimes we don't even know, so it's uncategorized. I think the struct is really big. The struct, I say struct because on the table we write it as a struct, but it's backed by a bunch of nested case classes. So yeah, it's pretty complex. In this code, we're actually using some cat stuff and so on. I mean, this one we went like a little bit far in it, but yeah, the maintainers is Scala people, so it's okay. But yeah.
Thank you.
Is it safe to say that most of this is for server-side metrics, just parsing logs, or do you have anything from clients that are also just having the measures on the client side as well?
No, it's especially Playback is client side. So we receive client stuff. If you like, the instant here is this instant on your device. If your clock is not correctly set, it's going to be different here.
So, so you implemented this measures library for all the clients as well, then?
Oh, sorry. The library is run on the server side, yes, but it just consumes data that is coming from clients too.
Got it. So how do you verify that the data is coming from client is going to match the case classes or whatever you're making server side?
Yeah, I see. Like, it's funny because this is exactly right now. Our logging system it's not like super schematized, and we're working on like having a new logging system that is schematized. But we have because devices they log in. Sometimes it's a long. Sometimes we have old devices that log a long into a string, so you have to parse the string and then get the long out of it. So we actually ended up implementing a lot of CRC parser and a decoder that handles like crazy cases and so on.
Got it. All right, thank you.
But we're working on a new logging system that is going to be like we're starting from scratch. So yeah.
Any more questions?
Hi. You listed in your future work, you're planning to build a UI.
Yeah.
Are you open to exploring Scala.js?
Oh, so I actually did build a UI in Scala.js back in the days. It was great. It was fun. But I'm not going to be the one building this. We are not like as in the Scala developers or the backend data engineers. I'm not going to build this UI. So no, I mean they're not into. If they want to use Scala.js, cool. But I'm not going to be the one supporting it. So yeah.
Well, next time.
Anyone else got a question? Yes.
Did you originally build it in Scala 2 or Scala 3? Was there a migration process?
Scala 2. No, I mean, yes. So what I showed you was in only Scala 3, but the repo, the idea of like creating measures library was Scala 2, and it was completely different. It was functions that accept any and gets out double. It was a double literally because it was like why double, because it was like any numeric can fit in there except maybe long, but at this point, and that was it. So we didn't have any like the play trace that wouldn't fit in a double. So it was very flat and so on. But we actually still have code like that. We're actually migrating everything into this more typed API. Yeah. Big migration. I mean, about the migration from 2 to 3, the code base itself before we introduced this whole API. My opinion is that the migration from 2.13 to 3 is easier than 2.12 to 2.13 because multiple reasons. You have first, the collection didn't change. The collection is the same. Scala 3 still uses the 2.13 collection. So you don't have binary incompatibility. And Scala 2.13 and Scala 3 outputs and read tasty. So we have dependencies on 213, and we're just using them as before. So to me, it was easier than migrating from 212 that has like basically breaks binary compatibility for 213.
Did you think there were any indispensable features in Scala 3 for this implementation?
Sorry, say again?
Any indispensable features?
Oh yeah, I mean for this API, yeah, we just cannot. So we have to have opaque type, because in this example, for example, you have ints. It's a simple type. Like I don't want. I guess you could do a case class with like one value in it, and extends any val for like performance reason. But then as soon as you run this into Spark and stuff like that, you have to like have encoders for it. I guess you have to have maybe encoders for it. But here we have generic encoders where it says any subtype of int, it will like encode it. So we don't have to have an encoder for each of the case class, for example, things like that. But for sure, types needs to be unique. Otherwise, your given is not going to get resolved.
Thank you.